Hello, students. Very good afternoon. My name is Ravi Ranjan Kumar, and I welcome you all to this session of uh, rotational mechanics. Today, we will be discussing the concept of toppling, and then we will discuss the definition of angular momentum, and then we will move on to the equation of moment, and then we will look into the dynamics of rigid body in case of purely rotational motion. Okay, so without losing any further time, let me share my screen with you people. So here we go. So let's start the discussion of toppling here. Okay, so we will start from an example. So let's say we have a block of mass m, okay, whose width is b and whose height is h, and we are applying a force F which is in horizontal direction and which is acting along the topmost line. Okay, and this block is resting over a rough horizontal surface, and here coefficient of friction is equal to mu. Okay, and we want to investigate like what should be the maximum value of F such that there is no toppling in this block. Okay, so let's investigate this problem. So before doing that, we must be able to draw the free body diagram of this block over here. So what all external forces will be acting on this block? So first thing, like it will be experiencing its weight, that will be equal to mg, and it will, point of application of gravity will be its center of mass or center of gravity, you can say. And apart from that, we will, this block, since it has tendency to move in rightward direction, so due to this rough surface it will be experiencing a backward friction over here. So there would be definitely an upward normal which would be balancing mg over here. But since we want to investigate the condition of no toppling, so that means the net torque acting on this block must be equal to zero about any axis. We can do this equation. Okay, so normal is definitely going to be vertically upward direction, but we don't know what would be the line of action of normal. So to do that, let's choose an axis. Okay, so let me use some other color pen. So I will be choosing, for example, this point P, about which I will be writing the equation of torque. I have chosen this point P to write the equation of torque because you can see that the torque due to mg and torque due to friction is going to be equal to zero about that point. Okay, so now you see about point P, this force F is going to produce some clockwise torque. Okay, so we need some other force to provide anti-clockwise torque to balance the torque due to that F. Okay, and that force will be normal. So in that case, in order to provide anti-clockwise torque, the line of action of normal will be at the right of point P. Let's say this would be normal, and let's say this is some x. Okay, so this is the line of action of normal. Okay, so now you see, the first we will be writing the force balance equation. So force balance equation along the horizontal simply gives us small f is equal to capital F, and force balance along the vertical direction simply gives us N is equal to mg. Okay, so this is equation number 1 and this is equation number 2. And if we balance torque about an axis passing through point P, so the torque due to capital F will be nothing but F into H, and torque due to normal would be nothing but N into X over here. So that gives us the value of X will be equal to FH divided by NUC. So now for no toppling, we can say the condition for no toppling means, see, this value of x, the line of action of normal cannot shift beyond this point over here, because if it shifts beyond this point, that will be not passing through the body. So the value, the limiting value of x would be, x must be less than equal to b by 2. So that gives us like fh by n got to be less than equal to b by 2. So that gives us f is less than b by 2h times normal, and where normal is equal to mg. So this is the condition for no toppling. Okay, so if the magnitude of this force F is smaller than equal to this quantity over here, we can say for sure that this block will not topple. So similarly, let's investigate the case of no sliding also. So no sliding condition means like friction will be sufficient enough to prevent relative motion between the block and the rough surface over here. So for that, F must be less than equal to mu n. And F we have already calculated from equation number 1. We can say small f is equal to capital F, and that must be less than mu times n, and n from the second equation is equal to mg. Okay, so this is the condition for no sliding. So when we merge these two situations, now you can see like if f is less than this quantity, no toppling. If f is less than this quantity, that means no sliding. So everything depends upon this coefficient over here, that is b by 2h, and this coefficient over here, mu. So depending upon which one is smaller and which one is larger, we will be able to comment that whether the toppling will occur first or sliding will occur first. Means if we are slowly increasing the magnitude of capital F, so which limit will reach first? So whichever limit will reach first, so that will give us whether it is toppling. Hello.
रविरंजन जी, आपका स्क्रीन हैंग हो गया लगता है। ओनली सिर्फ कैमरा पिक्चर दिखता है, लाइव में आपका स्क्रीन शेयर पिक्चर नहीं दिख रहा है। आई थिंक यू यू नीड टू रीओपन योर ब्राउजर और अल्ट्रा वियर। आप फिर से एक बार अल्ट्रा वियर खोल लीजिए। आई विल कनेक्ट योर सिस्टम एंड करेक्ट दैट इमीडिएटली।
अच्छा, ये स्ट्रीम नहीं हो रहा क्या अभी?
स्ट्रीम नहीं हो रहा है कि आपका कैमरा पिक्चर हैंग हो गया है। एंड
ओके,
आपका स्क्रीन, आपका जो भी एप्लीकेशन का स्क्रीन वर्ल्ड का या जो भी है वो नहीं दिख रहा है।
तो वापस फिर से शुरू करना पड़ेगा। आवाज आवाज सुनाई दे रही है? आवाज सुनाई दे रही है क्या?
आवाज मिल रहा है, आवाज आ रहा है पर वीडियो नहीं आ रहा है।
अच्छा, ओके, आई डोंट नो।
आप अल्ट्रा वियर खोल लीजिए प्लीज।
ओके ओके, हाँ, एक मिनट। पासवर्ड इज 2595।
ये आपका कैमरा पिक्चर स्टिल हो गया है।
प्लीज एंड इवेंट, वी विल स्टार्ट अगेन।
सो आई एम डिलीटिंग दिस व्हाटएवर इज
हाँ,
देयर ऑन
व्हाट?
बोर्ड।
ओके ओके।
सो यू आर लाइव अगेन।
ओ, ओके। Hello, sorry for some disruption. Okay, I think like there was some technical error. Okay, and my screen got hanged, and While having that, I started my lecture unaware of the fact. Okay, so let me start again. Okay, so I was discussing, first of all, let me close this window over here. So I was discussing the concept of toppling. So let me start again. So toppling. So we took the example of this block which was resting on a rough horizontal surface, and coefficient of friction between the surface and this block is mu, and the mass of this block is capital M, and its width is B and height is H. Okay, and we are trying to push this block with a horizontal force F, which is acting at the topmost of the block over here. So we wish to investigate the condition for no toppling. So in order to do that, we need to draw the free body diagram of this block. Hello? Application is not shared. Okay, I'm sorry. Like it is um, it, some error is occurring from the very beginning of this class. So I beg your pardon for this. Okay, so now this was the screen. Screen was not shared. So in case of toppling here, we have this block over here whose width is B and height is H. And we are applying horizontal force capital F, and this is the coefficient of friction being mu. We want to investigate the condition for no toppling. So in order to do that, we must be drawing the free body diagram of this. So the weight will be effectively acting along the center, at the center of gravity. So this is mg, and since this block has a tendency to move in forward direction, so there would be a backward friction F. Okay, and there would be a vertically upward normal exerted by the ground on this block. Okay, and definitely its magnitude will be equal to mg, but we do not know the line of action of the normal right now, because we will also be looking at the rotational equilibrium of this block over here. So in order to do that, okay, so let's try to write down the torque about this point P. Okay, this point P over here. So we have chosen this point P in order to write the equation of torque, because about point P, the torque due to friction and torque due to mg both will be equal to 0. So about point P, you can see the torque due to capital F is going to be in clockwise direction. So we need some force, in fact normal, we need the torque due to normal to be in anti-clockwise direction, such that it will be able to balance the torque due to this capital F. In order to do that, this normal will shift rightward to this point P, let's say by distance x. Okay, so now like we are ready to write the equation of forces as well as equation of torque about point P. So equation of force suggests that along the horizontal direction, small f will be equal to capital F, and along the vertical direction we can say normal will be equal to mg. Okay, and equation of torque about point P, torque about point P. The torque due to capital F will be nothing but F into H, and torque due to normal would be nothing but N into X. So that gives us X is equal to Fh by N over here. So now we were to investigate the condition for no toppling. So for no toppling, this x here must be less than this value b by 2, because the normal cannot shift beyond this point. So x must be less than b by 2, and the value of x is fh by n less than b by 2. So this gives us f is equal less than equal to b by 2h. Okay, and the value of n is basically mg. So this is the condition for no toppling, and similarly we can investigate the condition for no sliding also. So for no sliding means the friction is sufficient enough to prevent relative motion between the block and the surface. So in that case, F must be less than equal to mu n. So that gives us F is less than equal to small f is equal to capital F from equation number 1, and this is equation number 2, and capital N is equal to mg. Okay, so this is the condition for no sliding. So if we are slowly, let me insert some more pages over here. So sorry. So the condition, let me write over here, the condition for no toppling, we got F was less than equal to B by 2H times mg, and for no slipping or no sliding, it was F was less than mu mg. Okay, so if we are slowly increasing the value of f, so whether this limit will reach first or this limit will reach first is going to depend upon this coefficient or this coefficient over here. So if b by 2h is less than mu, then the condition for toppling will reach before the no sliding condition. So this will give you the condition for toppling before sliding, and this if b by 2h is greater than mu, then this condition of no sliding will reach first. Then that would be the condition for sliding before toppling. Okay, so this was very simple example for the toppling. Okay, so there is always a competition between toppling or sliding, at which one would be occurring first. So we have taken that example. Okay, after that, let's try to define one another physical quantity which would be very, very important in the discussion of rotational dynamics, and that quantity here is angular momentum. Okay, so we would be defining the angular momentum of a particle first. So angular momentum for a particle, let's say we have a particle of mass m which is moving with some velocity v, or you can say its linear momentum p is equal to mv. So we can define the angular momentum of this particle about some point. So let's say this is origin, and we want to define the angular momentum of this particle with respect to origin. In that case, we have to find out that what is the position vector of this particle m with respect to origin. So let's say that is r. So in that case, the angular momentum L, which is a vector quantity, would be defined as r cross p, the cross product of the position vector and the linear momentum vector. So that can also be written as m into r cross v. Okay, so obviously its magnitude we will be able to write it as mrv sine theta. Okay, and the alternate way of writing this is, geometrically you can see that if this angle is theta, so v will be having two components. This would be v parallel, and this would be v perpendicular, and here v perpendicular is nothing but v sine theta. So this can be written as mrv perpendicular as well. And the alternate way of writing this can also be, let's say we can define this position vector into two components, mutually perpendicular components. One is parallel to v, so this would be r parallel, and this another component would be r perpendicular. So r perpendicular here would be again equal to r sine theta. So alternate way of writing this can also be mr perpendicular into v. So depending upon the condition, we will be using either of these relationships in order to calculate the magnitude of angular momentum. And for the direction of angular momentum, we just need to use our right hand rule. The angular momentum's direction will be along r cross p. So if you curl the fingers of your right hand from r to p, the direction of thumb will be indicating along the direction of angular momentum. Like in this case, this is the direction of r and this is the direction of p. So the angular momentum here seems to be in inward direction. So that is the direction of L. So that is the definition of angular momentum for a particle. So let's take a few simple cases, okay, where we would be finding the angular momentum of a particle. So let's take this very simple example. So let's say this is x-axis and this is y-axis and this is origin, and this is some line, okay, parallel to x-axis, and its distance from x-axis is b, and some particle of mass m is moving along this line with velocity v naught. So we wish to find out the angular momentum of this particle about origin. Okay, so this definitely is the position vector, instantaneous position vector of this particle with respect to origin. So basically this angle you can say is equal to theta over here. So L, as we have defined, is equal to L is equal to m r cross v. So firstly we will be looking to write down the magnitude of angular momentum. So here we will be using this form of the formula, that is mr perpendicular into v. So mass of the particle is m, and it is very easy for us to see that the perpendicular component of position vector is nothing but b. So you can simply say mb, and the magnitude of velocity is nothing but v naught. So that is the magnitude of angular momentum. And about the direction, you can see the direction of position vector is this, and direction of velocity vector is this, and r cross v would be in inward direction. So here we are having, when we will be writing it in vector form, its magnitude is mbv naught and its direction is inward to the plane. So you can say that would be along minus k cap. So that is one very simple example. Let's take another example. Okay, the another example is that of a simple pendulum. So let's conical pendulum. So let's say there is a conical pendulum. Okay, and length of the conical pendulum is L, and this bob will be undergoing circular motion centered at a point on this axis. Let's just say this conical pendulum is rotating with angular velocity omega, and this mass of this particle is m. Okay, so here let's say this is r, or let's say capital R. So capital R, you can see if this angle is alpha, so capital R would be nothing but L sine alpha. Okay, and let's say this is moving in the sense of rotation is this. So this will be having a velocity in inward direction, and for example at this point this would be in outward direction over here, and magnitude of this v would be simply equal to r omega, or simply you can say L omega sine alpha. So we wish to investigate the angular momentum of this particle. So before finding out the angular momentum of this particle, we need to identify the point about which we want to find out this quantity. So let's say this point is A and this point is B. So first of all, let's try to find out the angular momentum of this particle, say about A. So about A, the magnitude of angular momentum, let's first try to find out. So the magnitude of angular momentum would be mass times r perpendicular. So r perpendicular is basically r, okay, and v, the magnitude of velocity, which is definitely equal to r omega. So that would be equal to m r square omega. And if we substitute the value of r in as a function of l and alpha, so that will become m l square sine square alpha into omega. So that is the magnitude of angular momentum. Direction wise, when we will be seeing, so the velocity is in inward direction, and the position vector is in radially outward direction. So r cross v. So r cross v here we will be seeing that will be turning into this direction. So this would be the direction of LA over here. So, or simply LA. So direction wise, if we are able to write, let's say this is, for example, Z axis. So LA can be written as M L square sine square alpha into omega. This is its magnitude, and its direction would be along z axis, so along k cap. Similarly, we can find out the direction of angular momentum of this particle about B also. So about B, if we are trying to find out, let's try to find out the magnitude of its first. So mass times r perpendicular into magnitude of velocity. So r perpendicular here would be with respect to point B, okay, would be simply equal to L, and its velocity is basically equal to r omega only. Okay, so L is and R is basically L sine alpha. So we can write it as ml square sine alpha into omega. Sine alpha into omega will be its magnitude. Looking at its direction, let me use some other color pen over here. Looking at its direction, now you see, let me draw the diagram again. Okay, so this is the direction of basically R over here. Okay, and the direction of velocity is inward. So r cross v, the direction of angular momentum will be in this direction. So angular momentum lb will be directed towards this. It would be perpendicular to uh, r vector as well as the v vector. So this is the direction of lb. So LB will be having two components over here. So this angle is alpha. So this component would be LB cos alpha, and this component would be nothing but LB sine alpha. Okay, so in vector form, LB can be written as, that would be LB cos alpha, that would be along, you can say r cap, and that would be lb sine alpha, and that would be along k cap over here. So you can see, like about A, the direction and magnitude both are constant. The direction of angular momentum as well as magnitude of angular momentum about point A both are constant, but about point B, as you can see, the magnitude of angular momentum is constant, but its direction is continuously changing, because the direction of this r cap will be changing continuously. So this is one of the example of conical pendulum. Let's take another example where we would be calculating the angular momentum. So this is the example of projectile. Say This is a particle of mass m, okay, which has been projected with some initial velocity u, making an angle theta with the horizontal. So its trajectory would be simply parabolic. So we require to find out the magnitude and direction of the angular momentum about O, let's say that is the point of projection after time t. So after time t, let's say the particle will come over here. So its velocity will become Vx and Vy respectively. So Vx we can write very well. That would be equal to simply u cos theta, and Vy we can write it as u sin theta minus gt. And looking at its position, okay, say its x coordinate will become simply u cos theta into t, and its y coordinate here will become u sin theta into t minus half gt square. So if we are writing the angular momentum about O, okay, so the angular momentum of this particle about O will be due to two components of velocities Vx and Vy. Okay, so the angular momentum here will be due to Vy, that would be in anti-clockwise sense. So the direction of angular momentum will be outward. So this would be Vy, and that multiplied with r perpendicular, that is x, so that we can say x times Vy, uh, m times x times Vy, that would be in anti-clockwise sense, so that you can say will be along k cap. And similarly, due to this Vx component, the sense of rotation is clockwise. So the direction of angular momentum will be inwards over here. That would be along negative k cap. And this would be basically minus m y times Vx into k cap over here. So basically you can say m into x Vy minus y Vx k cap would be the angular momentum. Angular momentum formula in component form. For example, if we have the position vector as xi cap plus yj cap plus zk cap, and its velocity is basically, let's say, vxi cap plus Vyj cap plus Vzk cap, then angular momentum L, which is defined as m r cross v, can be written in determinant form as m into I cap j cap k cap, and that would be x y z, and that would be vx vy vz. So using this formula could have get this result as well in this equation over here. So this was, in some cases we tried to find out the angular momentum of the particle. So now let's try to find out the angular momentum of a multiple particle system. Let's say angular momentum for a system of particles. So angular momentum for system of particles would be simply vector sum of angular momentum of the particle, each particle. So that would be simply summation of mi ri cross vi over here. So one another thing I want to point out here, since the angular momentum depends upon the choice of point about which this has been calculated. Okay, so what would be the relationship between the angular momentum calculated about two different points? So let's say we have 2 points A and B. Okay, and let's say this is ith particle, so this is mi. Okay, and its velocity is say vi. Okay, so this position vector, we can write it as position vector of ith particle with respect to a, and this is nothing but the position vector of ith particle with respect to b, and this vector we can say that is rba. Okay, so the angular momentum of a can be written as a summation of mi into ria cross vi, whereas lb can be written as summation of mi rib cross vi. So we wish to write down the relationship between LA and LB. Let's say, for example, LA, since we have written it as MIRIA cross VI, so that can be written like MIRIA can be written as uh, the vector sum of this as plus this. So that would be RIA would be nothing but RBA plus RIB over here, and that we can take cross product with VI. So this will give us summation of MI RBA cross VI plus summation of MI RIB cross VI over here. So this quantity RBA is constant, so RBA will come out of this summation sign, and that will be cross product with summation of MIVI, which is the total linear momentum of the system. You can say that is a linear momentum of the system plus, and this quantity is nothing but linear this is basically the angular momentum of the system of particle with respect to b. So this is lb. So we have got a wonderful relationship over here. Let me write it again. So la is equal to lb plus rba cross p over here. So this is the formula with the help of which we can find out the relationship between the angular momentum with respect to two different axes. And looking closely at this equation, one special case we can have that if somehow like p becomes 0, if we are looking at the system whose net linear momentum is equal to 0, so in that case we can say that the la will be equal to lb. So if the linear momentum of the system is 0, then the calculation of angular momentum does not depend upon the choice about which it is being calculated. So can you think of some system where we are having a linear momentum of the system equal to 0? So you might remember that in C frame what we always used to have that the linear momentum of the system, okay, in C frame we use the symbol tilde, remember? So p tilde is always equal to 0. So in C frame LA will be equal to LB. So this is the benefit of C frame that I have been always talking about. So if you are writing the angular momentum of a system of particle in C frame, you need not worry about which point you are writing the angular momentum, because it would be same about each and every axis. So that is a very, very important result, okay, that we will be using later. Another important result I want to share with you, since we have looked into the C frame. So if we know the angular momentum of a particle in C frame, will we be able to tell the angular momentum of system of particle in some other frame also? So basically, we are looking at this relationship and we will justify that also. So angular momentum of a particle in some other frame L can be written as L tilde. Okay, that is the angular momentum of the uh, system in C frame, plus that would be m times position vector of center of mass cross velocity of center of mass. So this is a very important relationship which enables us to find out if we know the angular momentum of the system uh, in the frame of reference of center of mass, which is very easy to find because it does not depend upon the choice of a point. Okay, so if we know this L tilde, we will be able to find out L using that relationship. Right now I'm just writing equation, and later on we will be using all those equation also. So let's not go into the derivation because we are really running short of time. Okay, so let's move on to the other concept. So this was about the angular momentum thing. So like that is very useful quantity, that will be very useful quantity in on upcoming sessions. Okay, so now let's move into the purely rotational motion of a rigid body. Like that is the thing we will be looking for. And before that, one more thing about the angular momentum I want to mention here is the relationship between the angular momentum and torque, and that is known as something called equation of moments. Okay, so L for a system of particles, we have already got it as mi ri cross vi. So if we take the derivative, the time derivative of this L, dl by dt, that will simply give us, or simply this, let's write it as ri cross pi. Okay, so this will simply give us, that would be dri by dt cross pi over here, plus the another term we will be having, that would be summation of ri cross dpi by dt over here. So this first quantity will turn out to be equal to 0 because dri by dt is nothing but vi, and pi is nothing but m into vi. So vi cross vi will be equal to 0. So we will be left up with the second term, which you can see is nothing but summation of ri, and dpi by dt is nothing but fi over here. So this is basically net external torque over here. So we have got this equation of moment, and that is very very useful and very very important. That is tau net external is equal to L, or dl by dt you can say. So that is very 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 important equation. So now let's look into the rigid body dynamics. So fixed axis rotation. So looking at the fixed axis rotation, let's say we have a rigid body which is constrained to rotate about this axis with an angular velocity omega. Let's say this is z axis. So any point on this rigid body will be undergoing circular motion. Okay, uh, about this axis having this radius as r. So this velocity, the velocity here would be v is equal to, that would be tangential, and its magnitude is simply going to be equal to r omega. So this is v over here. So if we wish to find out the kinetic energy of this whole rigid body which is undergoing purely rotational motion, so let's first look into kinetic energy. And let's not derive this equation simply. Say the kinetic energy would be equal to half I omega square, where I is the moment sorry, kinetic energy is equal to half I omega square, where I is the moment of inertia of this rigid body about z axis over here. So this is kinetic energy, and similarly angular momentum we will be able to write. Okay, so angular momentum about z axis only we will be able to write here, that would be equal to I times omega. So that would be the angular momentum. So these two equations which we have written, k is equal to half I omega square, and Lz, that is the component of angular momentum about z axis, that would be equal to I omega over here. These will be applicable for the fixed axis rotation, or you can say purely rotational motion of rigid body over here. Apart from that, the equation of moment which we have just derived, equation of moment, that was nothing but tau external is equal to dl by dt. For purely rotational motion of rigid body, L can be written as, let's write its magnitude, L can be written as I omega. Okay, so this will become I into d omega by dt. So that would be equal to I alpha. So tau external is equal to I alpha would be a very, very important equation for us. And next we are going to discuss problem based on that equation only. So let's do some problems over here. uh, Fixed x equation of moments. So so let's open another file. Equation. Okay, so let's look at this problem here. So what we are having here is we are having a uniform rod of mass m and length L, and initially it is at rest and making an angle theta naught with the vertical, and it has been released from this position. So initial angular velocity here is equal to 0, and the final angular velocity when it reaches at this orientation, when it is making an angle theta with the vertical, okay, we wish to find out that what would be the force exerted by this hinge. Okay, force exerted by this hinge on this rod at this instant over here. So the procedure of this question would be, first we will be looking to find out the final angular velocity. Okay, final angular velocity we want to find out. Okay, so in order to find out the final angular velocity, we will be using principle of conservation of energy in this situation over here. So as you can see that the center of the mass of the rod is moving from here to here. Okay, so center of mass is descending, so potential energy is decreasing, so at the cost of which the kinetic energy will be increasing. So gain in kinetic energy here would be equal to half I moment of inertia of the rod about the axis of rotation, you can say, is equal to ml square by 3 into omega square. Okay, and that will be equal to gain in or loss in potential energy. So that would be equal to you can say loss in potential energy would be mg L by 2 uh, into um, cos theta naught minus cos theta over here. Okay, so this is say equation number 1. So using this equation we will be able to get, omega naught. So now let's use some other color pen. So omega we have got, and using the equation of torque, okay, so at this instant what force is acting? So this is mg. Okay, so when we will be writing the equation of torque, and this angle is since theta, so this angle would be theta as well. So we will be having two component of mg. So that would be mg sine theta component over here. So the torque, we will be writing the equation of torque. We will be writing the torque will be mg sine theta into L by 2 is equal to I alpha. So that is ml square by 3 times alpha, we can say. So let's redraw this diagram over here. So this is the rod. Okay, so this is its center of mass. So center of mass is undergoing circular motion. So here it will be having two components of acceleration. One would be the tangential component at, and that would be equal to, you can say that would be L by 2 times alpha, and alpha we have managed to find out using this equation, and its centripetal component would be AC. Okay, and AC would be nothing but omega square L by 2 over here. Okay, so since we know the acceleration of center of mass using F is equal to mac equation, we will be able to find out this hinge force over here. Okay, so this hinge force, you can say, so we'll be having a radial component, let's say that would be fr, and it would be having some perpendicular component or tangential component, let's say that is ft, and apart from that it will be having its weight mg, which could be resolved into two components. So that would be mg sine theta, and that would be mg cos theta over here. So writing the equation of force along the radial and tangential direction, what we can say that along the tangential direction it would be mg sine theta minus ft is equal to m times at. Okay, and along the radial direction the equation would be simply equal to fr is equal to, that would be simply equal to, or fr plus mg cos theta would be the force over here, and that would be mass times centripetal acceleration, that would be m omega square L by 2 over here. So solving these two equation now, since we know the value of at and AC, the value we have already written, we will be able to find out the value of FR and the value of FT. The value of FR turns out to be half mg into 3 cos theta naught minus 5 cos theta, and ft will be equal to 1 by 4 mg sine theta. Okay, so this is one of the problem, and the another problem I want to discuss over here is this one. Okay, so here what we are having is a rod of mass m and length L, okay, which is initially suspended with the help of two strings, and this rod is initially in horizontal equilibrium. Okay, so when this rod is cut, when this string is cut, so this rod will be free to move. So at that instant, we wish to find out the angular acceleration of this rod as well as the tension in this string. Okay, these two things we wish to find out. So how are we going to approach this problem over here? Okay, so this is the center of this rod. Okay, so the first thing first, let's try to find out the angular acceleration of this. So when we are using tau is equal to I alpha equation, this equation we must be writing mostly about an axis passing through center of mass, because in an uh, accelerated body, as we will cut this string, this rod will accelerate, so all the points will have some acceleration. So when we will be writing the equation of torque, so that will be in about any point, it would be non-inertial frame of reference. So in that case, we have to consider the torque due to pseudo force also. So if we have to consider torque due to pseudo force, the benefit of finding out it about center of mass is like the pseudo force will produce zero torque about an axis passing through center of mass, because the pseudo force will itself be passing through the center of mass. So in this type of situation, it is always beneficial to write the equation of torque about an axis passing through center of mass only. So let's say about center of mass, the angular acceleration is alpha. So we can write the equation of torque over here. So the force that is acting is mg, but mg will not be producing any torque here. So the torque due to this T we can resolve in two components. The perpendicular component would be T sine theta, and that multiplied with L by 2 would be the torque about center of mass, and that will be equal to ml square by 12 into alpha. So that will give us this L and L will get cancelled and this 6 will get cancelled. So alpha would be equal to nothing but T sine theta divided by, or 6T sine theta divided by ml. So we have got the relationship alpha as a function of t. We are still required to find out t. So how are we going to do that? Okay, so when we will be looking at this rod in center of mass frame, so in center of mass frame, it will be undergoing circular motion. This point over here will be undergoing circular motion. So it will be having a tangential component AT and a centripetal component of acceleration AC. So tangential component of acceleration would be nothing but L by 2 alpha, and its centripetal component of acceleration will be equal to omega square L by 2, which would be equal to 0. Okay, because it has just been released, so its value would be 0 over here. So this would be the tangential acceleration, so that is at. So now uh, here when we will be looking at this, okay, um, and acceleration of center of mass will be having two components as well. Okay, so acceleration of center of mass, since the force acting on this would be in this direction as well as this direction over here. So let's remove this, um, since its value is 0. So this let's say is something ax and this is ay. So the acceleration of this point in ground's frame of reference would be vectorially added. So this would be ax and this would be ay. Okay, so this angle is theta, so this angle would be theta as well. So what we can say, like since this point has zero velocity, so the component of acceleration towards the string will be equal to 0. So the component of acceleration towards the string, if we equate, so that would be nothing but ay minus at sine theta, we can say that would be equal to ax cos theta. Okay, and equation of force we can write. The equation of force would be nothing but on center of mass, mg along the vertical direction, that would be mg minus t cos theta will be equal to m times ay, and along the horizontal direction it would be t sine theta is equal to max. So using equation number 1, equation number 2, equation number 3 and equation number 4, when we will be solving all these, we will be getting t is equal to mg sine theta divided by 1 plus 3 sine square theta, and alpha we would be getting it as 6g sine square theta divided by L into 1 plus 3 sine square theta. Okay, so in today's lecture we solved some problem of equation of moment here also, but this lecture I think like was technically not good. We got struck in the beginning, and we lost a lot of minutes here, and we were kind of in rush in order to complete all those things. So I will try to make up for it in the next lecture. Okay, thank you very much, thank you very much for joining. हेलो सर, अगेन while एंडिंग द इवेंट ऑल्सो ये हैंग हो गया है। यहाँ पर सिस्टम बहुत हैंग हो रहा है, मुझे मालूम नहीं, आज का लेक्चर तो पूरा ही बर्बाद हो गया। हाँ, ऑल्सो आई एम नॉट एबल टू एंड द इवेंट ऑल्सो। मैं अभी ले लूँ क्या ऑनलाइन ये डेस्कटॉप. No application is running, and this computer, this laptop, I only use for this purpose only. I do not use